Cool. All right. If I can just get everybody's attention, please. Thank you. Welcome back to another exciting session of 374U Urban Stormwater. We've got a great new module for you today. So today you're not going to need your computers. It's just going to be a normal lesson. Essentially what we're going to do is, last week I got you started on your course projects. So we're going to take kind of a turn back to hydraulic design for this next week. We're going to look at culverts this week, and we're going to look at detention basins. And then after I cover those two topics, essentially the rest of the course is going to be your design project. Okay, so just for this week, we will be covering culvert design and kind of the formal procedure that's used in industry for culvert design. Okay, so a couple quick announcements before I get started. Homework 4 was due last night. Homework 3 has been graded. Homework 5 will be posted shortly, so I'll probably post that today or tomorrow. This is going to be a shorter assignment, much like homework 4, and it's just going to be on culvert design and detention basin design. So this is a week-long homework assignment. And I've also posted homework 6. So I'll get to this in a second. So that's, you may have noticed that I uploaded homework 6. That wasn't a typo. So I've actually uploaded this ahead of time because it's more of a longer term assignment, and I wanted to give you kind of a head start on it. So I'll get to that in a bit. Third, I wanted you to remember to submit your HECRAS in-class assignments by tomorrow. Those are group assignments. One thing I wanted to note about the HECRAS in-class assignment number 2 in particular, so I got many questions about what specific kind of tables to turn in for your low water crossing. Really, the important part of this assignment is to be able to identify your particular low water crossing and what's happening at that site. So the particulars of the table that you turn in and the velocities and all that, we're not going to be checking really carefully what the exact values in the tables are. I really just kind of want you more broadly to understand what your site is in particular, because in some cases it can be ambiguous. And then second, what's the extent of the flooding problems at your site? So that's really the point of this assignment. So that will be due tomorrow. Tomorrow at 11:59 p.m. And I wanted to make one final note on excused absences. So just remember that if you're requesting an excused absence, for one thing, please remember to copy Becky on any email that you send to me on excused absences, because Becky is handling the actual logistics of the absences. Remember to follow up. So, in the attendance policy, if you're requesting an excused absence, you either need to attend the Zoom live stream of the course, or you need to watch the recording and then send an email confirming that you've watched the recording. So remember to do that. And also note that excused absences are intended for kind of 3 main reasons. First would be things like family emergencies. Second would be things like illness. So I don't want you coming to class if you're sick. And third, professional development. So for instance, if you need to attend an interview somewhere, or if you have some event with your job that requires you there, those are all good reasons for excused absences. So when you're requesting an excused absence, just remember to mention your reason for requesting the excused absence, okay? Are there any questions on those things before I move forward? Any questions? Questions on the HECRAS in-class assignment? No? Okay, cool. So before I move on to our main topic today, I wanted to go through homework 6. So I've uploaded this kind of to give you a head start. This won't be due until November 15th. So it's about 3 weeks from now. But essentially this homework assignment, it counts as a normal homework assignment, but it's essentially giving you the guidelines for you doing your preliminary design. So this will essentially give you the opportunity to get a head start doing your preliminary designs that will end up in your final project report. Okay, so I wanted to go through this and just kind of give you a heads up on what that will entail. So this is an assignment that you'll turn in as a group, but each member of the group will need to submit independent preliminary design. So for instance, when you turn in the homework, you'll have sections for problem 6.1, problem 6.2, problem 6.3. So you include your preliminary design under that heading. If, for instance, 2 people are doing culvert and channel modifications, you'll submit under problem 6.1, the first student, their independent preliminary design, and then the second student's independent preliminary design. So you're encouraged to work together, but each of these preliminary designs have to have a clear lead. Okay. There's essentially 3 different options. There's the culvert and channel modifications. I'll talk about each of these in a bit more detail. There's the culvert and channel modifications. There's the detention basin design, and there's the land cover design. So I want at least one group member to work on the land cover modifications. I want at least one group member to work on the detention basin design. And then because most groups are 4 to 5 people, I want 2 people working on the culvert and channel modifications, each with their own independent design. Okay. Okay, cool. And note here, because the detention basin and land cover modifications will require a bit more work than the culvert and channel modifications, you'll get a little bit of extra credit in your final project grade. So it won't be a lot, but those two design problems will be a bit more difficult, and so there'll be a little bit of extra credit if you choose to work on those. So essentially, this week, just coordinate with your group who is going to work on which preliminary design. And just discuss and decide amongst yourselves who will do each one. Okay. Are there any questions? Any questions so far on this assignment? Yes.
So this assignment is still on our end, or are you saying it's good?
So you'll coordinate when you're doing this assignment, because you need to decide, for instance, who's going to be working on the detention basin, who's going to be working on the culvert and channel modifications, and you also need to coordinate to understand, what's going on at the site. So based on your HEC-GRAS model, but the designs themselves that you'll be submitting will be independent. So each design you submit needs to have a clear lead attributed to it. Are there any other questions on that? Yes.
Not quite sure I understand. So, we have to have 2 independent culvert and channel modifications, but then say someone else does 6.2, is that allowed to be shared between the group? Or will that be completely independent? Sorry, to what extent are we allowed to work together?
You're allowed to work together on the project, but when you submit the design, it needs to be attributed to a primary lead who worked on that design. So you can work together, and I do encourage you to work together because it's a group project. But for the preliminary designs that will be submitted in this assignment, there needs to be a clear indication of who was leading that effort.
There needs to be at least 2, or
so for the detention basin, there will be 1 person in charge of that effort. For the land cover changes, there will be 1 person in charge of that effort. And then for the culvert and channel modifications, there will be 2 people working on culvert and channel modifications, but you will have 2 independent proposed preliminary designs. And then when it comes to the final project, you will essentially collate these designs together, select which ones you are going to include, and kind of create a finalized design based on that.
So for the submission from work 6, say we have to work on 2 different 6.1, Sam does 6.2, can we use Sam 6.2?
Yeah, it's a group submission. Yeah, it's a group submission. Cool. Was there a question, Samantha?
Okay.
It was your question? Yeah, so it's a group submission. So for instance, if there's 2 people working on 6.1, you would put in, Calvin And then, the other person who worked on that one is a separate preliminary design. Okay. Cool. Are there any other questions on this? So this is, again, this is due kind of in mid-November, so you'll have time to come talk to me and iron out any issues you may have. But I wanted to give you a heads up on kind of the contents of this assignment. Okay. So I've listed kind of guiding questions that'll help you through the design process. So the culvert and channel modifications will primarily be done in heckgrass. And note the goal here is to modify the culvert and or bridge and or channel to try to meet those Austin DCM design requirements that you discovered in the in-class assignment. So essentially this will be modifying the heckgrass model, modifying those geometries to try to meet the Austin DCM requirements. For the detention basin design, this will be done mostly in HEC-HMS because you'll essentially be designing a detention basin to try to capture extra inflows. So there's multiple ways of doing this. You can design a detention basin that's upstream that essentially just removes some of the rainfall from upstream contributing area. In previous semesters, many students implemented what are essentially diversion basins, where you'll have kind of a diversion coming off of the main channel that will fill up a detention basin, which will then reconnect back to your channel downstream. So there's kind of a lot of freedom how you can go about this, but it'll essentially involve kind of siting your detention basins, simulating it in HEC-HMS to figure out how it's going to affect the flows into the heck-grass model. And then from that, you can see how it affects the water surface profile. And the land cover changes, this will also be done primarily in ArcGIS and HEC-HMS. So what you'll be doing is downloading land cover data, figuring out, what the contributing area to your low water crossing is, and then making modifications to the land cover data to change effectively the curve number and try to reduce the amount of runoff. And that'll primarily be done through ArcGIS in terms of the planning, and then HEC-HMS in terms of the simulation. Okay. Great. And I wanted to reiterate. So this is a group project. So I don't want you not collaborating with each other. So you're definitely encouraged to collaborate. But when you go to submit your designs, each one will just have a primary lead that should be attributed. Okay. So yes, this is a group project, and I really highly encourage you to work together. Okay. Cool. Okay. Are there any questions, concerns, comments, hot takes? Okay. Cool. Well, if you have any questions about this assignment, come to see me in office hours today or Thursday. I'll be posting homework 5 a little bit, and that will be, again, a smaller assignment. But I did want to give you a head start working on homework 6. Great. Any other questions on course logistics?
So just to kind of clarify, homework is what we're going to be working on next week.
Yeah. So today and Thursday, we're going to be doing culverts. Tuesday of next week, we're probably going to be doing detention basins. And then after that, and up until November 15th, that will be in-class work on your projects. Yeah. Okay. Cool. Any other questions? No? All right, cool. Well, then let's get started. We have an exciting topic for you today. So last week, we took our first steps at working on the course project by analyzing a low water crossing in heckgrass. So you'll be using that for your course projects. It's also just a really important tool in general in hydraulic design. This week, we're going to take a step back and we're going to look at one of the most important parts of stormwater hydraulic design, which is culverts. So this is a really important topic because culverts are everywhere. Culverts are ubiquitous. And if you're working in the field of hydraulic or stormwater design, you will probably work on a culvert at some point. So it's important that you understand kind of the standard procedure for analyzing and designing them. Okay, so first, before I get into the design procedure, I just wanted to give a quick overview of culverts, kind of what they look like and what they're for. Okay, so I got a quick slideshow. Let me see if I can. Yes. All right, cool. So as I mentioned, culverts are ubiquitous in urban stormwater design. Many of you submitted pictures of culverts for your stormwater photo contest just because, you know, they're fairly noticeable and they're everywhere. I have a couple different examples of culverts. They come in many different sizes. They can be relatively minor culverts like the one you see up on the right, or they can be very large ones like Owen's photo in the bottom right, or this photo of the culvert near the stadium on campus where you have kind of a monstrous culvert with these huge energy dissipators. So they can vary a lot in size and scope. But the primary purpose of culverts, no matter what size they are, is pretty much the same, which is essentially to act as conduits that convey stream flow through underneath roadways or other obstructions. Okay. So culverts provide a way of allowing flow under roads. This is probably their primary use. The simplest culverts can be buried pipes like the one shown here. And note that the wall of the pipe here is rather thin. So this is a relatively small culvert. And the wall of the pipe can potentially be crushed by a truck. So it's often important to bury culverts below ground so that the forces are circumferential enough that the pipe doesn't get crushed. Culverts built close to the surface typically require a stronger structure like this one shown here, or just lighter design loads. We won't be getting too much into the structural properties of culverts, but it's an important thing to keep in mind. And different shapes of culverts kind of have different advantages or disadvantages. So circular culverts are generally used for smaller flows where the flow might slow to a trickle, whereas box culverts, as shown here, are typically used for larger, more consistent flows. Okay, and often they are constructed with more reinforced concrete. So often these are more structurally robust and meant for heavier traffic. An important thing to note about culverts is they're often precast and moved into place. So often box culverts are made from these precast concrete sections. And then during construction project, they're moved into place via a crane. And for this reason, they're almost always cheaper than a bridge. However, hydraulically, they're generally easier to block and pose a greater restriction to the flow going through. So you might be wondering, what's the difference between a culvert and a bridge? Does anyone want to venture a guess? Oh, first of all, do you think this is a culvert or a bridge? This is a culvert? Yeah, I would probably call this one a bridge. It can be hard to say sometimes, and there's really two main ways in which bridges and culverts operate differently. In one sense, it's just based on the dimensions. So bridges, National Bridge Inspection Standards classify a bridge as any structure with an unsupported span of 20 feet or more, which is probably, this is probably a bridge based on that definition. But they also operate differently in terms of the hydraulics. So culverts are typically designed to operate fully submerged, at least on the upstream end, whereas bridges are not. So bridges will typically have problems if they're submerged. Okay, so they're a little bit different both in terms of dimensions and in terms of how they're supposed to be used. Culverts are primarily hydraulic structures that are meant to convey water underneath, whereas bridges are kind of more of a transportation structure. Okay, cool. So I showed you kind of a quick overview of what different culverts look like and kind of what their purpose is. So culverts kind of have complex hydraulics just because there's many different ways in which the dimensions of the culvert and the flow conditions can change how they operate. So we're going to actually need to spend a couple different lectures examining them. The equations for the design are a bit more complicated than things we've looked at earlier in the course. So I just wanted to note that. Let's talk a little bit about the overall design procedure for culverts. Okay. So the basic idea is to design the dimensions of the culvert to meet a given headwater condition and a design discharge. So I'll just repeat, the idea is to design the dimensions of the culvert. So for a circular culvert, that might be the diameter. For a box culvert, that might be what are called the span and rise, or the width and height, in order to meet a given headwater condition and design discharge. I'll talk a little bit about what headwater condition means in a little bit. Okay, so the design procedure is as follows. We start by knowing a necessary design discharge. And an allowable headwater condition. Okay. All right. We may also know the desired tailwater condition as well. I'll talk a little bit about what these terms mean. What do you think I mean by headwater condition? Yes. Exactly. So we'll show kind of diagrammatically what this looks like, but the headwater condition refers to the depth of the water upstream of the culvert, and the tailwater condition refers to the depth of the water downstream of the culvert. And generally, we want to design for the headwater condition because that'll determine whether the roadway gets overtopped or not. Okay, we don't want the roadway to be submerged. Okay, so given these design conditions, we need to design the dimensions of the culvert. And typically this will be the vertical dimension. Although we may need to also design both the width and the height. Okay, so this would be things like, if we're dealing with a circular culvert, this would be the diameter. Okay, we may also need to design other aspects of the culvert. So we may also need to design the material. So what material is going to be used? So this could be either concrete, corrugated aluminum, or some other type of material. We need to possibly design the shape. So whether it should be circular, whether it should be a box culvert, whether it should be an arch culvert. And we may also need to design the inlet type as well. Okay. So this is the general design procedure for culverts. We start by knowing a design discharge and an allowable headwater. We design the dimensions of the culvert to meet that headwater condition for a given design discharge, which generally comes from something like a storm event of a given return period. We may also need to design the material, the shape, and the inlet type. So quickly before I move on, let me just show you different inlet types for culverts. Here's a couple examples of, oops, wrong button. Okay. I'll just show you this slide here. So there's a couple different types of inlets. Let me get here. So up on the top left, that's a relatively familiar culvert that you may have seen before. So this would be just a general projecting barrel type culvert. Often this is the case for corrugated aluminum culverts, circular type culverts. Another common one is this upper right one, the cast in place concrete head wall and wing walls. So this is the common design you might see, and there's actually a reason why it's designed this way. Why do you think we might want an inlet that contracts? Why do you think we might want an inlet that contracts and has a smooth transition in width? Do you have an idea?
So the slow velocity.
It might be. So we'll get back to this later. There's a specific reason, and think perhaps to something we looked at earlier in class. Yes. It would decrease head loss, yeah, if you have a smoother transition. I'll give you the answer a little bit later on when we get to what are called inlet control culverts. But just think about that. And then in the bottom right, there's also an important case to note, which is a culvert with the end mitered to the slope. So this will have the equations for the hydraulics for this particular case will be a bit different, especially for the case of inlet control. Okay, so those are just different culvert inlet types that affects the ultimate design equations that we might use. Great. Okay, so with that, let's talk a little bit about the anatomy of a culvert, what a culvert looks like, and what these different terms mean, headwater and tailwater, and so on. Okay, so let's look at the anatomy of a culvert. Okay, and I'm going to draw a culvert here. So first, let me start with the ground surface. I have a ground surface that goes down. And here's the downstream end. I'm going to have a culvert here. Here's the top of the culvert. And then on top of the culvert, we're going to have an embankment. Okay, so let me just label the different parts of this diagram here. As I mentioned, this is the ground surface down here. We'll just say that this is the ground. This here is the embankment on top of the culvert. And on top of the embankment, you will generally have a roadway. So let me draw the roadway here. Okay, and let's say that we have some water surface. Let's say our culvert is submerged at the upstream end. So we have a water surface here. And this depth here, the depth of the water above the ground at the upstream end, this will be our headwater depth. And I'm going to give it with the name HW. This is the variable name that's usually used in the hydraulic design manuals. HW is the headwater depth. Okay, we'll also have some tailwater at the downstream end. So let's say it's not fully submerged to the downstream end. The depth here is TW. So this is the tailwater depth. And on the inside of the culvert, we will have kind of a water surface profile. Let's say it goes down and looks something like this. Okay, so our culvert is submerged at the upstream end. It has some flow going through it, and it has a tailwater at the downstream end. And we will have a circular culvert here. Let's just call the diameter of this culvert D. Okay, in addition to that, we also need to know the length of the culvert. We'll call this L. And we will need to know kind of the elevation of the bottom of the upstream end above our datum, which is the elevation at the downstream end. And I will just call this L times the bed slope S naught. Yes?
So an example problem to give us the L of culvert, it's not like the diagonal, it's the horizontal. Like,
Yeah, so we're defining it as the horizontal length in this case. Yeah. Good question. Thank you. Okay, so note here that HW, the headwater depth, just to be clear, this is the depth of the water at the upstream end. We can also have the headwater elevation. And this is equal to HW plus L times S naught, using the bottom as our datum. And we can also have the headwater head. Which is equal to HW plus L times channel bottom slope plus U squared over 2G. Okay, so we might have an energy grade line here as well, in addition to our hydraulic grade line. So this is our energy grade line. Okay, so just familiarize yourself with some of these terms here. Great. Are there any questions on kind of the general schematic of a culvert? Any of these terms that we're using? Any questions? Okay. Cool. So again, recall that in culvert design, the discharge through the culvert is generally specified. And we're designing the culvert diameter or dimensions in order to meet a specified headwater depth to prevent the roadway from overtopping. And there's two design procedures that we use depending on the particular hydraulics of the culvert. Okay, so there's two different cases in hydraulic design of culverts. The first case is called inlet control. And the second case is called outlet control. Has anyone heard these terms before in terms of culvert design? Anyone heard the terms inlet control or outlet control? So these terms essentially refer to they refer to the design procedure that we need to follow in order to analyze the hydraulics in the culvert. And they depend on the geometry of the culvert and the hydraulic conditions. But essentially the difference between them is as follows. So for inlet control, you have the condition that critical depth is achieved just downstream of the culvert entrance. Okay, so critical depth is achieved just downstream of the culvert entrance, and the flow is predominantly supercritical. So I'll just say flow is mostly supercritical throughout the length of the culvert. And this is by far the easier of the two cases to analyze. Okay, so why is this case easier to analyze? So what happens when you achieve critical depth near the entrance of the culvert? Think back to the problem on homework 1 you had with the flow coming out of a lake. You remember that in that problem, the critical depth was achieved near the mouth of the channel that was receiving the water from the lake. Now, in that problem, did you need to know anything about the properties of the channel downstream? Did you need to know the Manning's roughness or the channel geometry downstream? What did you need to know to solve the discharge in that problem? Does anyone remember? Sorry? So you need to know the height of the lake. So that would correspond to the headwater depth in this case. Where did you need to know the channel geometry? What part of the system did you need to know the channel geometry for? Right, which is the location where what occurred. Right. So if you have a section of the channel where critical flow is occurring, you know that there's a depth discharge relationship at that point. You can compute the discharge just based on the geometry in that section, and you don't need to know anything about the channel downstream. Okay, so for inlet control, we really only need to know the geometry where the critical depth is being achieved, and we don't have to worry about the conditions occurring downstream. Okay, for outlet control, it's essentially the opposite. So the flow under outlet control, the flow in the culvert is either pressurized. Okay, so it's either pressurized, meaning that it's submerged on both sides and completely full, and thus has hydraulics similar to that of a water distribution system or a pressurized pipe system. The flow in the culvert is either pressurized or subcritical throughout most of the length of the culvert. And this case is in general much more difficult to analyze and design for, because if you have outlet control, you need to essentially reconstruct the water surface profile throughout the entire culvert. You can't just look at the discharge and depth at a single point like you can for inlet control. You have to essentially perform a full water surface profile analysis to analyze the behavior of the culvert. So outlet control is the much more difficult of the two cases. All right. Are there any questions on these two types of culvert control before we move on? Any questions conceptually about inlet and outlet control? Okay, so let me give you a couple examples of what inlet and outlet control look like. First, let's take a look at inlet control. So these are different ways that inlet control can be achieved. So remember, inlet control is when you have essentially critical depth being achieved near the entrance of the culvert. So we have four different cases here where this can be achieved, and these are conditions that you might see in the real world. So in the first example, A, neither end of the culvert is submerged, but critical depth is achieved just downstream of the entrance, and it's supercritical throughout most of the barrel, with the flow approaching the normal depth at the outlet. Okay, so if you have a long culvert in particular, generally you will approach the normal depth at the outlet. Okay. So another case is B. In this case, the outlet is submerged, but the inlet is unsubmerged. Nevertheless, you have critical flow being achieved just downstream of the entrance, and the flow is mostly supercritical throughout the barrel, but you have a hydraulic jump near the end, and the culvert ultimately ends up being submerged on the downstream side. Okay. C, you have the case where the inlet is submerged and the outlet is unsubmerged, with critical flow, again, achieved near the entrance and supercritical flow throughout the culvert. So this is probably the most typical case that you'll encounter in practice, which is submerged at the upstream end with inlet control and unsubmerged on the downstream end. And then in the last case, we kind of have an unusual case, you have a vented culvert that is submerged on both ends, but nevertheless, you achieve critical flow just downstream of the entrance, and thus you get supercritical flow throughout most of the culvert. So this is still inlet control, but you still end up getting submerged on both ends because you have a hydraulic jump near the outlet. So this is a relatively unusual case, but what's kind of the common factor between all of these cases of inlet control? What's the common factor? Right, critical depth at which end? Right, so the common factor between all of these cases, you can get various types of water surface profiles, you can get hydraulic jumps and all kinds of stuff, but the common factor is that critical depth is achieved near the upstream end. Okay, so that's very good. Okay, so let's take a look at a couple examples of outlet control. These can be kind of varied, but again, they do have a kind of a general common factor. So A is a common design condition you might encounter. You have both the inlet and outlet submerged, and the culvert is essentially completely pressurized. Okay, so you're getting pressurized flow throughout the culvert. So this is a common design condition. Situation B, you have that the exit is submerged, the inlet is unsubmerged, but you still have subcritical flow throughout the culvert. For C, you have that the inlet is submerged, the outlet is unsubmerged, but you still have subcritical flow throughout the culvert. D, you have, this is probably the most typical design condition. You have that the entrance is submerged, the outlet flows freely with a low tailwater, and it's subcritical throughout most of the barrel. Okay. And E, you have that neither side is submerged, but you have subcritical flow throughout most of the barrel. So that's also another common design condition. So the ones that are most common are A, where you have pressurized flow, and then D and E. But all of these situations could potentially occur. What is kind of the common motivating, what is the common factor between all of these different cases? Yeah, so it's either that it's pressurized or you have subcritical flow throughout most of the barrel. And that determines essentially the equations that you're going to need to solve to determine the hydraulics throughout the culvert. Okay, great. Are there any questions on inlet and outlet control and the difference between them? So again, this largely has to do with what equations we need to use to analyze and solve the hydraulics throughout the culvert. Yes.
With some of these, will it usually be like a culvert will either be the outlet control, or it kind of also depend on the skill of that?
It could, yeah, it could depend on the discharge as well. So I'll have to think of an example where that could happen, but yeah, it's essentially whether you achieve critical depth at the upstream end or whether it's fully submerged. So I can imagine, like, if you increase the discharge enough, you may end up with the culvert just being overwhelmed and being pressurized on both sides, but it would operate under inlet control for a different discharge. So that is possible, yeah. So good question. Any other questions on inlet and outlet control? I know the terminology can be a bit strange, but essentially the whole point of this is it determines which equations you need to use in your design procedure. Whether you can just look at the critical section or whether you need to reconstruct the entire water surface profile. All right. Cool. So let's look at the case of inlet control. We're going to look at the case of inlet control first. On Thursday, we're going to look at outlet control primarily. Of the two, inlet control, as I mentioned, is the easier of the two to analyze. Okay, so let's look at inlet control. So within inlet control, there are essentially three cases that can happen. So culvert design can be kind of complicated because even within inlet control, there's multiple cases. Even within outlet control, there's multiple cases. Often what you'll have to do is follow kind of a flow chart to figure out which equations to use. For inlet control, we have three primary cases. The first is that you have a submerged inlet. Okay, so you're submerged at the inlet. The second case is that you have an unsubmerged inlet. And the final case is transitional. So it's between submerged and unsubmerged. And I'll talk about what that means when we get to it. But essentially what's going to happen is that we have to interpolate between submerged and unsubmerged equations. Okay, so with that, let's talk about how we can actually analyze and design the dimensions of a culvert under inlet control. I'm going to look at the unsubmerged case. The submerged case is relatively similar, but I'm just going to show you kind of the procedure for the unsubmerged case first. And what we're going to do is we're essentially going to apply the energy equation between the upstream end of the culvert and the location where the critical flow is achieved. Okay, so we're going to apply the energy equation between the upstream end and the location where critical flow is achieved. All right. Awesome. Okay, let's go through with this procedure. I'm going to draw out our culvert again. And we're going to look at how we can apply the energy equation to analyze the hydraulics of the culvert under inlet control. Okay, so let me draw out my culvert again. Oops, let me draw that a little better. Okay, so here's our ground surface. I'm going to draw our culvert in again. Okay, we have our embankment on top of the culvert. All right, and also I'm going to also draw kind of the top view of the culvert. We're looking at it from kind of a bird's eye view. So this is our top view of the culvert. Let's say this is the upstream end, and this is the downstream end. So we got a culvert with kind of those wing walls at the inlet and at the outlet. Okay, so we're going to get a contraction. Okay, let me just define a few terms here. Let's say we have our water surface coming in. Let's just say it's, we're looking at the unsubmerged case, so it's underneath the top elevation of the culvert. So we have water coming in. We have water coming into a contraction. We have water coming into a smooth transition in width. And let's say the water at the upstream end is subcritical. What's going to happen when that water undergoes a smooth constriction in width? Think back to homework 1. What's going to happen to the water surface as it approaches a smooth constriction and width, assuming that it's subcritical at the upstream side. Exactly. Cool. I bet no one was expecting that was coming back, right? So the water surface is going to go down. Okay. And in this case, we have inlet control. So the water surface will go down until it reaches the critical depth. And once it hits that point, it's going to become supercritical and continue down like so, where it will become the tailwater. All right, cool, very good. So let's kind of label our different terms here. We're going to apply the energy equation. So we have that our depth at the upstream end we'll call H1. Let's say that this is our datum here. And this distance here we'll call Z1. And now we're interested in applying the energy equation between the upstream end and between this point here where the critical depth is achieved. Okay, so we'll call this depth here H2, which will be equal to the critical depth HC. We'll call this elevation here Z2. And let's also specify the velocity. So we have the velocity of the upstream end, we'll call that U1. The velocity at the critical point we'll call U2. And there's one final piece we have to note here. This distance here between the upstream end and the point where critical flow is achieved, we'll call this distance delta X. Let's just assume we can somehow know what this distance is. Right? Great. So we've got our depth of the water, we got our bottom elevation, we have the velocity. Let's go ahead and write out the energy equation for this section. So let's write out energy equation. I'm going to start a new page here. All right, and help me out with this energy equation here. So we have, on one side, we have our energy at point 1. So we have H1, the depth, plus, what else do we have? Z1. What else do we have? U1 squared over 2G, very good. Okay, and at the location where the critical depth is achieved, what do we have? We have H2, we have Z2, and we have U2 squared over 2G. And we also have head losses. Okay, what do you think those head losses incorporate? What do you think the major head losses are there? Sorry? Right, so the frictional losses, right? So that includes the frictional losses. What else does it include? Yes?
Losses from the transition.
Yeah, so the contraction, there's a contraction loss, especially when you're encountering, a very sharp contraction. Yeah. So HL, this, I'll just write this includes friction and I'll just call them local losses. So contraction in this case. Okay. So let's go ahead and subtract Z2 from both sides. First, let's just look at Z1 minus Z2. How can we express the difference between Z1 and Z2 in terms of the variables we know? Let's say we know the channel bottom slope. No, it's not quite H2. So it will be we look at the difference between Z1 and Z2, it'll be, right, so it'll be delta X times S naught. Okay, so we can subtract Z2 from both sides. And what we end up with is H1 plus delta X times S naught plus U1 squared over 2G is equal to H2 plus U2 squared over 2G plus HL. And note, I'm gonna kind of re-express this. Instead of saying H2 and U2, I'm gonna say HC and UC, because we know that these are the critical depth and the velocity at critical flow conditions. So I'm going to write them as HC and UC instead. Okay, so let's rearrange this. We're interested in the headwater. Which of these terms corresponds to the headwater depth? H1. So let's isolate H1 on the left-hand side. All right, H1 is equal to, I'm just going to group these terms here, HC plus UC squared over 2G plus the head loss minus U1 squared over 2G minus this term associated with the elevation difference, so S naught times delta X. Okay. And now I'm going to do something kind of odd here. I'm going to divide all of these terms by the diameter of the culvert. This is the way it's typically expressed in the culvert design manuals. They will usually express everything in terms of the headwater depth divided by the diameter of the culvert. So I'm going to go ahead, I'm going to divide everything by D, which is the diameter of the culvert. Okay, so let's see, what here do we know and what do we not know? So we can conceivably figure out what the critical depth and the critical velocity are. But we don't know what delta X is, and we definitely don't know what this term is here. So what we're going to do is we're going to need to employ some empirical approximations. Okay, so we're going to apply empirical formulas to determine each of these terms. So this term and this term here with the head loss, we are going to apply a couple of empirical formulas to estimate those two terms because we can't determine them analytically. Okay. So first, let's take a look at this term here, which includes the head losses and the velocity at the upstream end. So what will be used in the standard culvert design procedure is the following approximation. So the head loss minus the velocity head at the upstream end divided by D. We're going to assume it equals an expression of the following form: K times quantity K sub U times the discharge divided by the cross-sectional area times the diameter to the 1/2 power raised to the power M as in Mike. Okay, so basically this is stating that the head loss and the velocity head terms at the upstream end are a function of the discharge. It's some nonlinear function of the discharge. And these parameters K and M, these essentially come from lookup tables that correspond to culverts of different shapes and inlet types. Okay, and that will help determine what our local losses are. So let me just note here, K and M are found via lookup tables. And KU is a constant that depends on the units. So this is equal to 1 for US units and 1.811 for SI units. Okay. And there's one more assumption we're going to make. So we have this term essentially describing the velocity, head, and local losses. We also need some equation to describe this term here, which depends on the distance from the upstream end to the location where critical depth is achieved. So to do that, we also use another empirical equation. So let me just write this out. We have that negative S naught times delta X over D is equal to a term that we'll just call Z. And this is going to be equal to negative 0.5 times S naught for most inlet types. And it's going to be equal to positive 0.7 times S naught for mitered inlets. Essentially, these different inlets affect the distance at which critical depth is achieved. So that's what this equation is showing. Okay. And with that, we can write out the full design equation for culverts with inlet control that are unsubmerged on the upstream end. I'll just give you a second to finish writing if you have done so. Well, are there any questions on this? Any questions on this procedure? Yes.
What's a miter inlet?
So if you go back to that picture here, it's this one here on the bottom right. So it's mitered to the slope, and it just affects the distance at which critical depth is achieved. Okay, so let's go ahead and write out the inlet control design equation. And I will write it out first for the unsubmerged case, which is what we just derived. And then I'll also write it out for the submerged case. Okay. So this is for the unsubmerged case. We have that HW divided by D, and I'm just going to write HWI to indicate that it's inlet controlled. We have that the headwater depth divided by the diameter of the culvert is equal to, I'm going to write capital HC over D. So this is, let me just write this out. HC is going to be equal to the specific energy at the critical section. So this is little hc plus UC squared over 2G. Okay, so this is the specific energy at the critical location. Okay, so for the unsubmerged case, the headwater depth divided by the diameter is equal to the specific energy at the critical section divided by the diameter plus that expression we just derived for the head loss terms. So that's K times KUQ divided by AD to the 1/2 power, all to the M power plus Z. Okay, so this is for the unsubmerged case. For the submerged case, I'll just go ahead and write this out without deriving it because it would take way too long. But for the submerged case, it's similar. You'll have the head water depth divided by the diameter is equal to C times KU Q divided by AD to the 1/2 power squared plus Y plus Z, where Y and C are again lookup table coefficients that depend on the culvert and inlet type. So I'll just write that out. C and Y are determined via lookup table. Cool. Let me just give you, I'll show you what these lookup tables look like. So this is what a set of coefficients might look like for culverts. So it depends on the shape and material, the inlet type. And then you have the coefficients for the unsubmerged and in this case, it's just unsubmerged, but you have the K and M coefficients. So you would determine it via lookup table.
So if it was like a rectangular culvert, what would D be?
It would be the vertical dimension. So D always refers to the vertical dimension. And then typically in like the classical design for culverts, you would just assume a width and then just design for the vertical dimension. But you can also design for both of those at the same time, just iteratively. Right. So but D essentially refers to the vertical dimension. All right. And I just want to make a note here. For unsubmerged and submerged, it doesn't necessarily mean that it's literally submerged or unsubmerged. For this design procedure, there's a specific condition that has to be met in terms of these equations to determine whether it's submerged or unsubmerged. So I'll write that out here. So it is unsubmerged if the following expression holds. So if KU Q divided by A times D to the 1/2 power is less than or equal to the 3.5, it's considered to be unsubmerged. It's considered to be submerged if that same expression is greater than 4 or greater than or equal to 4. Yes. Yeah, without the M value. Yeah. So I could get rid of that parentheses, but yeah. Okay, so this is how we determine if it's unsubmerged or submerged. If this term is between 3.5 and 4, you essentially linearly interpolate between the unsubmerged and submerged cases. And I'll write that out, and that will be the last thing that I do today. I had an example, didn't quite get to it today. Yes. Is the expert on the C term too? No.
In the submerged case.
So yeah, that's just C. That's oh yes, that's a 2. Yeah, that's a 2. I'll write that bigger. This is squared. Try to make it not look like a Z. Okay, there you go. 2. Okay. And just so that you have this, so we're going to do an example. We come back tomorrow for the transitional case. Did anyone not finish writing that down? Oh, it's still going. Oh, yes.
What is A again?
A, that's the cross-sectional area. Yeah. Yeah, so these are, right, yeah.
Or like you might, yeah.
It might not be
It
fully flowing, yeah. Yeah, so this is, as we'll see when we do the example, this is an iterative procedure. So you'll need to start with a guess of what D should be, compute the headwater depth and see if it meets your desired design criteria. Yes,
So the cross-sectional area, is that of the flow or of the culvert?
of the flow, yeah. Yeah, of the flow. Oh, actually, sorry, that's incorrect. A is the full cross-sectional area of the culvert barrel. Sorry. It's hard to know sometimes with these empirical equations what it actually means. But yes, A is the full cross-sectional area of the culvert barrel.
So it is the area that's made.
Yeah, unless it's a square or another shape. All right. Last thing I'm going to do is I'm just going to write out the case for the transitional case where you have this term being neither unsubmerged or submerged. Okay, and in that case, you will essentially interpolate between the two. Okay, so this is for when it's between 3.5 and 4. I'll write out the equation first. You have that the headwater depth divided by the diameter is equal to 1/2 times 4 minus KUQ divided by AD to the 1/2 power times the headwater depth divided by the diameter using the unsubmerged equation plus 1/2 times KUQ divided by A times D to the 1/2 minus 3.5 times HWI divided by D using the submerged equation. So essentially you would go back to the equations on the previous slide. You would compute the headwater depth using the unsubmerged equation. You would compute the headwater depth using the submerged equation, and you would use this to linearly interpolate between the two. Okay. And this is for KUQ divided by A times D to the 1/2 power is less than 4, but greater than 3.5. Cool. That's all I have for you today. We're going to do an example of inlet control culverts when I come back on Thursday, and then we're going to look at outlet control.